uploaded it a couple of hours ago. So look in your localization and mapping folder, and you'll find a Kalman filtering 1, which means there's going to be a Kalman filtering 2, and that will be the end of the localization and mapping topic. That will happen on Monday next. But let's go through Kalman filtering 1. So here it is. Now, as I said yesterday, sometimes it's harder to explain concepts when you don't go through all the math, right? But if you do the math early, then that can be a turn off also. So it's better to have an idea first, and then if you're interested, you can go into the math later. All right, let me put it in projection. So, again, localization is a two-step process. Count the steps and then look up. That, counting steps is like a blind person, and then the blind person grabs a knob or a refrigerator handle or a furniture. So, it's 2 steps always. So you can use either odometry or IMU to count your steps, and then you can use a camera or LiDAR vision or GPS for looking up. So you have many options, and that's why you have so many variations of the method. Now, what that study showed, with the ellipses growing in this direction and not so much in this direction, that is an odometry model. So from the counts, you have to figure out where the robot is, and it's simple geometry. I told you, right, that if the right wheel rotates a certain amount and the left wheel rotates a certain amount, it's quite easy to figure out where the robot is. And that simple odometry model, already exists, and it's built into ROS actually. Okay, now it's based on probabilistic techniques. So the formal derivation of Kalman filtering will start with a theorem known as Bayes' theorem. So Bayes' theorem, B-A-Y-E-S, he was one of the most famous scientists ever. Bayes' theorem is used in medical diagnosis. So for instance, when you have a new blood test, like COVID test, they come up with what? False positive and false negative. That means if the test is positive, there is a fraction of people who don't actually have COVID, right? And the other thing, the opposite is also possible. You may have COVID, but it may say you don't. Every test has these 2 aspects, false positive and false negative. You want false positive to be 0, right? You want false negative to be 0. Never happens. It's not going to happen in this lifetime. So there's always a small amount of error. If you make one more, the other one will go down. And if you turn around and make this more, the other one goes down. So it's a trade-off. So there are many situations in life that subscribe to this principle. Bayes' theorem is used in figuring out those numbers. What will be the false positive and false negative, based on they catch like 1,000 people and give them the vaccination. That data is used, and Bayes' theorem, to figure out exactly what those numbers will be. So if Bayes' theorem tells you that the false positive is going to be 50%, it's a useless test, right? So that's how they judge whether this vaccine is useful or not, because you can't really have a 50% false positive or false negative. So that's how you test whether a test is useful or not. Otherwise you throw it out. You might as well just guess COVID, not COVID. There's no need to give a test for that. So I wanted you to be aware that there is an underlying theory based on Bayes' theorem that we are not covering. So there are 3 variations of localization. The most popular, the first one is Markov localization. It's computationally very intensive. That's why many people don't use it. Why? It's because it tracks all possible robot poses. So for instance, assume that we have this tiling system on the floor, right? Roughly 12 inches by 12 inches. I'm used to talking in inches because I've lived in the West for so long. But whatever, centimeters by centimeters. So I want to know whether the robot is in this tile or that tile or this tile or this tile, right? So the Markov localization assumes there is a finite probability between 0 and 1 of the robot being in any one of those tiles. Of course, it can't be where an obstacle is, but you get the idea. It says, okay, every tile has a probability. And as you move, it's carrying that entire set of points. It's saying, okay, if the robot is here, what is the new probability of where it will be? And that's why it is so computationally intensive. It's maintaining multiplicity of positions. Imagine if we did that on the VIT campus, how many of these tiles there'll be, and how much effort the computer has to put in to keep all those alive. By the way, you're not going to keep all those alive. When it finally comes, somebody asks you where is the robot, you're going to pick the largest probability, right? You're going to go through all those tiles and say, okay, which is the largest probability? And they're going to say most likely it is there. Sometimes you could be wrong, but that's how probabilities work, right? If it's 0.9 in one tile, the chances are that you're going to be right with that particular guess, right? So that's how Markov localization works. It keeps all the probabilities alive. Now, don't assume that every tile is not going to have a zero probability. Some of them will truly be zero. Because if I'm here, and what is the probability I'll be on top of a tile on the other side of VIT campus? That's not likely. So in practice, you won't be carrying all the tiles. You'll be carrying like a finite set. But the point is, it's more than one. You keep multiple possibilities alive because you have more chances of getting it right. Right? You're keeping all of them alive. So there are more chances of being right. On the other hand, cabinet filtering, it uses only one probability. And so you better not lose the robot because there's only one tile you're monitoring. And if that falls away, that's it. You're in the dark because you don't know where the robot is now. So cabinet filtering is based on only a single robot pose. So pose XY theta. And it uses a Gaussian distribution. Markov does not require any probabilistic distribution. Kalman is based on an assumption of Gaussian distribution for x, y, and theta. And yet it works. I told you, 99% of all boats, planes, ships, etc., they use Kalman filtering. It's built into all boats these days. Planes use it too. Except nobody knows where that Malaysian Airlines plane went, MH370. So, because the guy turned off everything. So, it's basically a sensor fusion technique. This is the best way to look at it. The explanation I'm going to give you, if you look at it as sensor fusion, that's the best chance of understanding. You're combining two sensors, right? What are they? The odometry is telling you where you are, and then you're getting a GPS signal, and that's telling you where you are. Neither of them is perfect. So you can't average them, right? Averaging would be giving the same weightage to two measurements that have different degrees of error. So you can't average it. You have to fuse the two sensors with a more sophisticated probabilistic technique. That's what Kalman filtering is. You can't average them. So it is statistical sensor fusion. Now particle filtering is the most recent arrival on the scene. It requires a lot of memory because what it does is it does not use probability density distributions just like Markov, but it maintains a cloud of points. So it says the robot could be here. So it basically is carrying a cloud of points representing where the robot could be. And the cloud is moving and moving. And as it moves, the cloud becomes more uncertain. But then you look up, and then there's more certainty. Then as you move, it becomes more uncertain. Then you look up, but it's a cloud you're carrying. And so it's memory intensive. So it's the latest entrance into the field, particle filtering. So I'm going to give you a little bit of a review of Gaussian distribution since you may not have experienced it in the recent past. So it's also known as a normal distribution or the bell curve. It covers, as I said, many statistical phenomena in the real world, like heights of people and when you die, which of course differs by country. So there's almost a Gaussian, actually it differs by ethnicity and race and so on. So there's almost a Gaussian for each race, etc. And And for men and women, it's different. It's completely characterized by two parameters. That's the beauty of it. Kalman filtering, right, is computationally the least expensive, because the Gaussian enables you to characterize the robot's position by just two numbers for each x, y, and z. So each of them is characterized by two numbers, right? So you have the mean and the variance. The variance is the square of the standard deviation. So the curve will come up again on the next slide. So if you move further away from the mean, there is less chance of that occurring, right? If you move closer to the mean, there's greater chance of it occurring. So this is the mathematical expression for the Gaussian. If you plot it in MATLAB, it will look like the bell curve. That's why they call it the bell curve. So here are several bell curves. The left, the set of curves is particularly interesting. I'll get to that later. But here is the Gaussian, and you can see its particular property. So here is the mean, right? And you're one standard deviation away, two standard deviations away. And you can see that, is it 68%? 68% falls within plus minus sigma of the mean. So most of it is concentrated here. It kind of falls off rapidly. So this part, which is beyond 1 sigma, 2 sigma, is only 3.35%. It's symmetrical. So on the other side also you'll get a 3.35%. The chances are becoming less and less as you go further away. Now, this is interesting because he has drawn three Gaussians, the blue, the red, and the yellow, with mean 0. The mean doesn't have to be 0, it can be anything. But notice what happens here. So, which one has a larger standard deviation? The blue curve, the red curve, or the yellow curve? The yellow curve, right? It's flatter. Now, would you like the robot's x position to be characterized by this, or this? Which is most uncertain? The yellow. So, if you localize with odometry, what will happen is an initially sharp curve, you'll see this, an initially sharp curve will start to get washed out. It will get flatter and flatter and flatter. So when I say odometry falls apart, what happens is initially you're very certain of where you are, and then you're less certain, and then you're least certain, and if you keep going, it will become virtually flat, which means that you don't know where you are. So that's the problem with relying on odometry. It becomes more and more uncertain. You know what happens if I find the area under this curve? Let's say this represents the position of the robot along the x-axis. What will happen if I integrate and find the area under this curve? Integration is area under a curve. So if I take this represents x, because we have x, y, and theta. Let's assume this represents x. What is the area under this curve? So the area under the curve is what? The chance that the robot is anywhere from minus infinity to plus infinity, right? The robot has to be somewhere, it didn't disappear. So it has to be 1. So if you integrate under the curve, it's 1. Right? So the robot is somewhere, but you don't want a flat, low Gaussian because that's not telling you much. Now here is another Gaussian, green, with mean of minus 2. And with variance, square of standard deviation of 0.5. So this is fatter than the red one. The red one has a variance of 1. No, red one is fatter. Sorry, red one is fatter. 1 is larger than 0.5, twice fatter. So if it gets fat, it gets short. Because the area is 1, right? This is very important to understand. The area is 1. So if it gets shorter, it has to get fatter. If it gets thinner, it will get taller. Do you understand this about Gaussians? So if you squeeze it this way, it will become tall. If you pull it this way, it's going to get short. You don't want the robot's odometry to become, Gaussians that are shorter and shorter and fatter and fatter. And that's why you need to look up. You need to look up and, correct it. And therefore, that's why they rely on a single Gaussian, unlike the Markov method. They rely on a single Gaussian because they are sure they will not let odometry fall apart. So you have to get that GPS refresh before the odometry falls apart. And then you're okay. You can manage with just one position. So it tracks just one robot position carefully, because if you're wrong, you're in trouble. So often you characterize it as sensor fusion or multi-sensor fusion, because I can fuse odometry, IMU and GPS. I can do that if I want more confidence. So now you have to fuse between three quantities. So that's the redundancy I was talking to you about. Human beings, use redundancy without even thinking about it. So we're trying to make computers use more information, just like human beings. All right, now, so we're going to start with a static case. In the 25 minutes we have, we'll make good progress, and then on Monday we'll take up the dynamic case, which will finish off localization and mapping. So, now initially I'm going to say, this is crazy, because the static case, I assume the system is not changing, which means the robot is not moving. That means I'm looking up, looking up, looking up, and you're saying, what is going on here? Because if the robot is not moving and you're constantly looking up, what are you hoping to achieve? Because I'm establishing one part of the Kalman equations. On Monday, the robot will move, and then we'll combine that equation with whatever we learned from here. So it's one step at a time. So now we're just going to be looking up, looking up, looking up, the robot is not moving, right? And then we see how to treat those equations. So we measure the static state repeatedly, and that's equal to repeated perception. Look up, that's called perception, because you see, look up and say, okay, McDonald's, right? So that's called perception. So repeated perception updates. Also, we're going to work with a one-dimensional variation, because if I do all three, x, y, theta, then I have to introduce matrices, and then you'll begin to hate me. So we'll do just one to establish the concept, right? There are equations that do all three together, but we have to start small, not jump into the motion straight away. So we go into a small swimming pool first and practice swimming. So we are not going to go with the actual robot problem yet. We're going to assume that we're measuring a resistor. So let's say we have a 100 ohm resistor, and I measure it, I measure it, I measure it. It's not changing, okay? I just measure the same value of the resistor. One question is, what is a 100 ohm resistance? Is there such a thing as a perfect 100 ohm resistance? No. So if you pick 100 ohms from a box and you pick another 100 ohms, you'll get different values actually. Secondly, with the same resistor, you measure with the same meter, you get different values. Now, don't tell me that, hey, the number is not changing. That's because they're not showing enough numbers, right? If the meter had enough accuracy to show you additional digits, then you will see that every time I measure, I measure the resistance value, I'm getting a slightly different value. It happens. I told you, when you are young, you tend to believe that instruments are perfect. There's no such thing. So when you repeatedly measure, the same instrument will give you a different reading, because there's uncertainty. So let's assume that the resistance has a 1% tolerance. So let's consider that to be the standard deviation. So imagine a Gaussian, right? 100 is here, and the standard deviation is 1% of 100 ohms, which is 1 ohm. So you can imagine a Gaussian for the particular brand of resistor. Okay, now the measurement instrument, an ohm meter, you know what an ohm meter is? It measures ohms. That has a resistance, that has an error of 3 ohms standard deviation. So 3 ohms standard deviation is 9 ohms squared sigma, right? Variance is sigma squared. So that would be 9 ohms squared. So 3 ohms is sigma. And again, this is a statistical characterization. Imagine a Gaussian for the meter. Okay, now, so I'm going to assume X is the actual resistance value. We do not know the actual resistance value. We know model state only because it's artificial. But nobody knows the real position of a robot, right? So we don't know what the real resistance value is, but it's needed in the mathematical development. So that is what we are trying to estimate. We are trying to figure out what is the truth, as we do in religion, right? We try to figure out what's the real truth. So X, you can never get. You can get closer and closer to it, but you'll never be able to get to X. You're actually seeing X through the meter reading. So multiple meter readings are giving you a different view of the same X. X is not changing. It's the same X, but why is the meter reading different each time? Because there is like a fog. So this is the error. Epsilon is not known precisely, because if you know epsilon precisely and you know y precisely, I can get X as y minus epsilon. Epsilon is a statistical characterization. Epsilon is not a precise number. It's a sample from a distribution. So that epsilon is itself, shifting around. So look at it this way. You're trying to always see the real value through a fog. The fog, this epsilon, is clouding X. You're only able to see Y, not X. But you're seeing X through this fog. So we'll quickly get to the Kalman result, because we're not deriving anything. I used to derive it once upon a time, but I gave up on that. So there is something known as the Kalman gain. B is the Kalman gain. Let's stop here and look at how it's constructed. So it's the variance of X, sigma X squared, over the variance of X plus the variance of the meter. So the Kalman gain, named after Kalman, is the variance of X. And remember what X is? X is the actual resistance value. Let's go back one more. It is the 100 ohm resistance with a 1% standard deviation, right? So 1 squared happens to be 1. Maybe I shouldn't have used the value 1, because you want the square to be different. Maybe I should have used 1.5 or something. This number is okay because 3 squared is 9, not the same as 3. In any case, this is called the Kalman gain. And so now, the estimate, that means I look up and I come up with a new value for where the robot is, what the value of the resistor is. It's done according to this equation. Now let's just stare at it for a few seconds. So the new value is the old value, is that clear? Plus the Kalman gain times the difference between the measurement and the old value. Let's say it again. The new value, the new estimate, is the old estimate. Whatever you thought was the best before you looked up again, right? Remember, we're looking up, looking up, looking up. So we have an old estimate. And after each new lookup, I replace the old value by a new value, which is the old value plus the Kalman gain times the difference between the new measurement minus the old value. Now, if B is 0, if B, the Kalman gain is 0, and we'll see when it can be 0. If B is 0, then the new estimate is the same as the old estimate, right? When will B be 0? Let's look at this. So B is 0. When I say B is 0, I'm saying ignore the meter. That means don't trust the meter, it's useless. Right? B is 0 means don't ignore the meter. So when would B be 0? Can you tell me from here? So one situation is meters much more accurate than accuracy of stated resistor value, right? So when the meter is much more accurate than accuracy of stated resistor value, then the sigma square is blowing up. You can't trust the manufacturer, right? So then won't you trust the meter? And what about the opposite situation? And the meter is useless. You trust the manufacturer, right? And so what this equation tells you, and this is formal derivation, it's not Kalman making it up. This is formal derivation gives you this. It says, it's a combination of the two. And depending upon B, I'll trust one more than the other. In general, you will not have a situation where you say throw away the meter or throw away the manufacturer's result. You'll be somewhere in between. It's always going to be somewhere in between, right? In practice, it's going to be somewhere in between. Why would you go with a meter that's completely useless? Unless it's broken. So this is the way to combine the two. This is sensor fusion. You're seeing sensor fusion in one dimension by Kalman theory. So the new value is the old value plus a correction here. Now I want you to expand this out. If you have a piece of paper, expand it out and combine the two x naughts together and rewrite it. Can you do that for me? I'm going to do it on a blank Word document page here. So right here. Except I do it here because I'm blocking the equation. I do it here and then I show it to you. I'm not going to do the hats and the subscripts. So x1 equals, if I combine the x naught and the minus bx naught, I'll get x naught times 1 minus b, correct? And then I'll get plus by1. So let me show you what I have. I'll blow it up really big. And I'll show you. So this is what I got. I hope you got the same thing. I expanded it. This is the way that Kalman equation is written, because it looks like, okay, I'm taking the old one and just adjusting it a little bit. I'm adjusting it by this much, right? But if I expand it, it has a lot of intuition built into it. You agree? This is the equation. So, what do you think is the range of B? Just look at it. Can B be larger than 1? Not possible, because you have sigma x squared and you have sigma x squared plus something, and this is a positive quantity. So B cannot be larger than 1, right? It has to be between 0 and 1. B has to be between 0 and 1. So isn't that beautiful? Because you're basically saying a piece of y1 and the remaining piece of x naught. So if B is 0.5, what is 1 minus B? 0.5. Then you're saying half and half, right? You're averaging. But I told you, averaging in general is not good, because you don't know that these two measurements are equally bad or equally good. So if B is 0.2, then 1 minus B will turn out to be 0.8. So it's such a beautiful result that Kalman came up with rigorously, not by guessing. So it's a piece of this plus a piece of that. You know, that's how you expect it to be. You have two sensors which are imperfect. How do you put it together? This is how you do it. So the two extreme cases, B goes to 1. So when B goes to 1, it means that sigma e squared, epsilon squared is 0, very small. Or the other way around, you have B going to 0, which means that this is much larger than that. Sigma e squared is much greater than sigma x squared, will lead to B greater than 0. That means ignore the meter because it's broken or it's useless. Of course, you'll never have those extremes. You always have two results that have a chance of contributing to something. Now, if you got that, we are making good progress. I'll show you one more result that stems from this. And I think, if a few minutes are left, we'll stop there, because getting into the dynamics today won't help. The dynamic case, where the robot is moving, won't. If I do 10 minutes of it, I'll, because 5 days will go by before the next class, we're going to, again have to repeat that. So it is a result based on formal derivation, not just intuition. So here's the beautiful part about it. Is that result that is based on synthesis God's word? Is that the true result? It's not. It's just the best estimate for it. Is that clear? So getting the true result is different from getting the best estimate for it. You'll never get the true result in the real life. It's just not possible. Can you tell me what your height is precisely?
176 centimeters.
But is that precise? It's not. if I measure it 5 times, I get 5 different results. One day you might be a little bit like this because you're tired, and one day you might be, standing up straight. So no measurement in the real world is perfect. That was my point. And that you accept numbers as if they are perfect, but they are not really, perfect. So what Kalman said was, there's no reason to believe that each one of his results, his synthesized results, is the best. What he's saying is, overall, if you use that method, no other method will beat it. That's what he's saying. He's not saying each one of my results cannot be beaten by a better estimate. He's saying if you use this method over and over again, my method will be the best overall. And that's what it turns out to be. So here, ML estimate does not guarantee that each computed result is the best, only that on the average, the method gives the best possible estimate of many readings. Okay, here's the part that I wanted to finish. So, you know what this is? So, when you look up and take a new reading, right, and you come up with a new estimate, you can't use the old variance anymore because you have combined the old value with its sigma with a different sigma, right? Because you're using the meter. So therefore, the old variance has to be corrected because you have mixed it with a measurement. And Kalman derived that this is how you get the new sigma for X. It's a combination of the meter and what the manufacturer told you. Now the manufacturer's value is only valid for the very first update, right? After that, you forget about the manufacturer. You're only working with the previous one that needs to be updated. So only one step at a time. You don't worry about all the... This is one of the beauties of Kalman. Because it's a one-step update, it's very fast. It's not like particle filtering, it's not like Markov localization. It just goes so fast because it's recursive. That means you only need the previous result to get the next result. And then you forget about the previous result. So, Kalman showed that the variance is obtained by this. Now, it can also be written like this, but I'm not interested in that. This can be manipulated in that form. This is the form that gives you a lot of intuition. Now, how many of you remember how to combine two resistors in parallel? You remember that? R1, R2 by R1 plus R2? Do you remember that? So do you also remember that the equivalent resistance will be lower than the lower of the two resistors? Do you remember that? That when you combine 10K and 5K, the result has to be less than the smaller of 10 and 5, which is 5K. So you can think of this as combining two resistors, right? So this variance is the smaller of the two variances, isn't it? So doesn't that mean that every time I look up and get a new measurement, I'm actually improving myself, isn't it? Every time I take a new measurement, I'm improving myself. Because this sigma, this sigma is smaller than this and this. It's actually smaller than the minimum of these two. In our case, we had what? 1% and 3%, right? So it'll be better than the 1%. So that means if you go on measuring, now don't think that you reach heaven by continually measuring, because you'll never quite reach heaven. It'll get better and better, but after some time, the improvement will be less and less. Is that clear? So it's not like you're going to climb these steps to heaven. At some point, you'll be at 10,000 feet and not progressing anymore. But the beauty is, you will get better with that lookup operation. So Kalman showed that. So I don't have to, go through this because I basically talked through that. So these are the equations so far. Just the static case. First, you calculate the Kalman gain, which is the sigma previous plus the measurement, the new measurement. So calculate the Kalman gain, sigma squared previous estimate plus the meter. Meter doesn't change at all here, right? And then you do your update, the last one, plus we go back to writing it in the old form. Now, this is the form that is preferentially used. That is equivalent to this. It's really the same thing, but they write it this way. So, 3 equations for the static case of Kalman. There's 2 more. That's coming from the dynamic side, which we'll discuss on Monday. So basically, Kalman equation is a 5-set collection. So you go through those 5, and then you go through the 5, then you go through, when do you go through the 5? When you see, the robot is moving, right? So that's 2 equations. Then you look up, 3 more equations. And then you start moving again. No, actually the robot is continually moving. You're not stopping it to do the, it's done on the fly. But 2 equations plus 3 equations, 2 equations plus 3 equations. And that's what Kalman filtering is. It's very simple to implement. And as I said, most navigation systems in the world use it. It's built into the boat, the plane, and so on. So basically, you need the expected value of the resistance before any readings are taken. And of course, that's only the first time. Once you get into it, it becomes the previous one, which is this one here. The variance of this value, that's this one here. The variance of the meter readings, and that's it. You are ready to go. The only thing I'll say is, you have x, y, and theta. So you can't go with one equation, and you can't go with 3 equations. You can't say, I'll do one like this for x, one like this for y, and one like this for theta. It doesn't quite work like that, because there's something known as correlation. So x and y and theta can be correlated. In which case, if you do that, if you update it as 3 separate Kalman filtering sets, you'll be getting double counting. Because x and y and theta are related. So it has to be done as a matrix formulation. And that matrix derivation is quite complicated, actually. As I said, 20 years ago I used to do it, but then, it's hard to get the students to come along with you. So I just give them the results and explain and give examples. But it's a matrix equation because you can't just do it as 3 separate sets. So I think this is where it's a good point to, So the procedure is recursive, and that's why it's computationally efficient. You don't need to save all of the older readings. What is needed is just the previous estimate, the new measurement, and whatever it takes to find B. That is the sigmas. That's all you need. All of the past, every single item in the past is in that new estimate. That's it. All of that has been brought forward. So you don't need to remember the past anymore. And that's why it's computationally efficient. So I used to give a problem to the students and have them work out, we don't need to do that. But essentially, you can do some hand calculations. This is very simple, but the matrix equation, a human being is going to struggle with it. So I guess we did make it to the end of it. So we are in great shape. And next we'll consider the dynamics. So the dynamics doesn't mean the same thing as the, remember we said kinematic and dynamic? This is not the dynamic means the robot is moving. It's not the same dynamics as the word dynamics in robot motion. Okay, do you have any questions on the homework, or you finished it multiple times? So let me give you a quick piece of advice, just repeating old stuff. So you have this L, right? So what you have to do is, if you draw it on graph paper, you'll say, okay, I'm going to consider this as one circle, right? And then you're going to get an approximate reading of the radius. It can be approximate because when you run the program, you're going to adjust it anyway, right? So if a circle is like this versus a circle like this, which one has the bigger radius? Flatter or the sharp one? The flatter one, right? So just assume some value. You can fix it later, right? Then you say, okay, how much of the circumference do I have to trace? Because the robot's path is going to trace out the L, right? So how much of the take a guess. Maybe it's 1/10, right? So use a variable in the MATLAB program and put a variable there. First segment, maybe you can call it C1, circumference 1, meaning how much of the circumference, right? All right? So, how do you guarantee that the robot runs only for that circumference? Now, first of all, you have to realize the radius, right? How do you get the radius? Radius is equal to V by omega, right? Now, you can't put any value of, do you realize that multiple V and omega will satisfy the same radius? Do you want to use a V of 500 miles per hour? No, because the turtle bot should not go above 0.22. We are taking it up to 0.4. So what I would do is, if you want the thing to go quickly, choose 0.4. If something bad happens, we can drag the velocity down. So choose 0.4, calculate the omega needed to satisfy the first radius, right? Got it? So don't do it as numbers to numbers, right? Do it with symbols in MATLAB so that you can just change something at the top of the program and everything automatically changes. So now you figured out V and omega, right? Then if you know V and you want to go 1/10 of the circumference, isn't it easy to calculate the time for which you should run the robot? Because 1/10 of what is the circumference of a circle? 2 pi r, right? And let's say you want to go 1/10 of the circle. That's 1/10 of 2 pi r, correct? Divide by velocity, you will get the time needed to go around the circumference, right? Right? We studied this back in school. Correct? Everyone got it? You want to go 1/10 of a circumference. The circumference is 2 pi r. You know the velocity with which you're going around the circumference. You should be able to calculate the time to trace out that circumference, right? Now do it for however many segments you have, 6, 7, whatever, you know. Got it? And then put it in a loop. Each time, you know, you feed a new segment parameters in and run it. Now, you can stack it without doing a loop, but you know, that's not good programming practice. You know what I'm saying? Each segment, you know, you keep copying the runs. No, better to put it in a loop and then run it and then see what it looks like. And then you can say, okay, this part of the L is okay, but here maybe it went too long. And then you can adjust it. If you have everything in the form of symbols, then you can do it rapidly. And you can see new shapes, you know, being plotted out in odometry, and you can finish the problem in half an hour. Are you confident? You should be able to do it, right? Because the rest of it is gazebo setup and all that. I've already given you the program, so you can just copy all that gazebo, just change the IP address to suit your situation. Isn't that clear?
Yeah, I think so.
Yeah. Okay. Good luck.